My presentation هتكون بالإنجليش أول شيء, and it's more about the Milky Way and its mysteries. So just like the topic says, I'm gonna try to tell you what kind of research astronomers do to uncover the mysteries of the Milky Way, some of the mysteries at least, because as you know, understanding the Milky Way fully is something very challenging and almost impossible at the moment. And in astronomy, you have different fields, different research areas for those who are interested in research and in science. And one of those fields is what we call galactic archaeology. And galactic archaeology is the science in astronomy that tries to better understand the formation history of our galaxy, the Milky Way. And it's very similar to what archaeologists do here on Earth. I mean, archaeologists try to find fossils and signatures on Earth, and they try to use them to understand how Earth evolved with time and how civilizations came to what they are today. And it's exactly the same with galactic archaeology. Astronomers going in that field, they try to look for fossils and for signatures that were left behind during the evolution phase of the Milky Way. And this is what I will be sharing with you today. Some of the tools and some of the techniques that we use to uncover the formation history of the galaxy. Now, on any given day, if enough, you would have seen something like this. And this is what we call the Milky Way strip. Not only it's fascinating to watch and to see, but it also has very important and significant scientific implications, which means that like when you look at this strip, you would be looking at one of the arms of the Milky Way. And more importantly is that when you look at these clouds clumped here that are glowing and they have different colors, you would be looking at clouds of gases that are under collapse because of the force of gravity. And because they are collapsing, the temperatures and the pressures, it's going really up and it's reaching very high values, and this will eventually form new stars. So why is this important? It's because we are witnessing the formation and the birth of new stars. So if you have, good telescopes, you can watch these clouds, what we call nebula, and then you can try to understand how stars are formed and then apply it to our solar system to understand how our Milky Way, our sun and solar system was formed. So for the outline of what I'm going to be speaking about next, it's going to be divided into 4 short parts, I would say. The first one, I will talk a bit about the history of our understanding of the Milky Way and the universe. So how our perspective of the universe changed over time, from the Greeks' time all the way until today. And then I'll speak more about the evolution of the Milky Way as an example, and with a focus on the halo part of the Milky Way. And eventually I'm gonna end this with talking about new discoveries in the Milky Way. And this is what we call stellar streams with Gaia. And Gaia is a space telescope, which I will talk about later on. So if we start with the history of our understanding of the Milky Way, this would be, just an overview about different civilizations and how they thought about the universe. Now, humans in nature are curious. We are curious creatures, right? We try to ask questions and we look for answers. And we try to understand the nature that surrounds us. And once we understand the nature, we try to take advantage of that and advance, in our technology. And we move forward with innovation and so on. So just because people and, human are curious in nature, the Greeks had one thought, and they always had in mind that the universe can be understood logically. So in other words, if you can logically prove something about the universe, it has to be common sense. So for example, if you look at the night sky, if you watch the sun and the stars and the planets, you from Earth, when you look at them, they all seem to be moving around the Earth. And this is what made Ptolemy, thousands of years ago, to come up with the first model of the universe, and that is the geocentric model, which was a very simple model because it assumed that the Earth was at the center of the universe, and that all the planets and the stars are revolving around the Earth. Now, does this make sense? It does actually, and it's very logical because if you observe those objects tonight, they really appear as if they are moving around us. And this is what led to the geocentric model. And people at that time liked the idea of a geocentric model. They liked to be at the center of the universe. It kind of gave them a purpose, and it satisfied their beliefs and their thoughts and ideas and so on. Now, although this was wrong, this model is wrong, and we know today as a fact that it's wrong, but it was used, and it was believed in for more than 1400 years. And it was only until the 1500s that this guy, Nicholas Copernicus, he came and he presented a new model, and that model was what we call the heliocentric model, which is rather a corrected version of the geocentric model. So Copernicus thought that the universe revolves around the sun. So in this sketch here, this is the sun right there, and that Earth and the other planets and everything there is in the universe were assumed to be moving around the sun. And this is what we call the heliocentric model. Now, although Nicholas Copernicus suggested his model, and he tried to present it for everyone, but he didn't have enough proofs on one hand, and on the other hand, people didn't really want to believe in a heliocentric model. They'd rather stick to the geocentric one. And also at the same time, one should mention that people in the 15th century, they always thought that the universe is static. They always thought that the universe does not change. It has always been there. It will always be there, and nothing ever will happen during its lifetime. So there's no evolution, there's no change in the universe. And for them, the universe, they were, our Earth, the solar system, some of the stars you see in the night sky, and that's it. But of course, in the year around 1572, something new appeared in the sky. And that new thing, it just appeared in the sky. It was very bright, and then it took 18 months to fade away. Now, why is this important? It's because it contradicts with the vision we had for the universe. We thought the universe is not changing, it's static. But now we see a new star being born, and then it's fading away. So what was that object that appeared and then disappeared? Even if, like, Tycho couldn't really explain what that object was, but at least he was able to know that the universe is changing and evolving, and that there's something happening out there. What he was able to do, though, is he was able to find the distance to that object, and he realized that this object is really, really far away, further than we have ever thought. So we moved from a geocentric model to a heliocentric model, which is static, and now we realize that the universe is not static, but it's evolving. Now the question is, how is it evolving, and what's going to happen to the future of our galaxy? Now, Tycho had a student, or not a student, but more of an assistant. His name is Johannes Kepler. Perhaps many of you know about or heard of Johannes Kepler, but this guy gave us the laws of motion. He was the first one to talk about how planets move in space. He was like, planets move in space in ellipses and not in any other form of motion. So he gave us the 3 laws of motion. And around the same time, later on, the famous Galileo was finally able to prove the heliocentric model. You see, although Copernicus suggested this heliocentric model, but as I mentioned earlier, he wasn't able to prove it fully, and people did not really believe it. They weren't ready to actually adopt it and to believe it. And it was only until this guy used a telescope, he found some objects, and those were the moons of Saturn, of Jupiter, and he saw that those satellites were actually orbiting Jupiter. So for the first time ever in human history, someone has detected an object that was evolving around an object other than the Earth. And so this proved that the geocentric model is totally wrong, because the proof was right there. He could see stuff moving around other stuff. So it's not always about Earth. And this is how the heliocentric model, came in favor for people. Now, there was a great discovery, of course, by Galileo, and we still build on his discoveries and so on. And it was like Galileo said, hey, there are stuff moving. And he stopped right there. He couldn't really explain why those stuff were moving around Jupiter, why those satellites were revolving around Jupiter and not Earth or the Sun or any other object. So all he did was observe those objects, and it was enough to prove the heliocentric model. Now, people had to wait some more time for Isaac Newton to come up with the laws of gravity. And of course, this changed our understanding of the nature and of the universe that we lived in. And until today, we still use, the laws from Kepler and from Newton to actually launch satellites to space and to send rovers to Mars and to explore space and so on, right? And if you think of the force of gravity, I mean, the formula is rather simple. It actually gives you the amount of the forces that is in between two masses. So in other words, gravity is any force is actually the force that is exerted between two different objects. So if you have two objects next to each other, Einstein was able to give us a formula to calculate how much force is being created from these two objects, and they are proportional to the masses of the object, and they are inversely proportional to the distance between the two objects. But again, Newton continued what Galileo had said. He said, hey, there are stuff moving because of gravity. So this is what he added to science and to the history of astronomy, of us understanding the nature. But you see, he was able to calculate the amount of energy that is being created between two objects, but he really couldn't explain why would there be energy from the first place. So if you think, like, he could tell how much force is being exerted between the sun and the moon, because they are, they have a specific distance, each has a mass, so there's a force between them. This is what we call the force of gravity. He could give us how much force is being created, but he couldn't really tell why would the moon feel the Earth and why would the Earth feel the moon. I mean, in the end, there's empty space between them. How can they feel each other? And for that question to be answered, we had to wait nearly 200 years for Albert Einstein to come into the picture. And Albert Einstein, he spent a lot of time thinking about the gravity and what it could be, because for 200 years, people were using Newton's law without really understanding them, and without understanding how can different planets exert forces on each other. And this is when Einstein, he presented the special and general theory of relativity, and this is where he introduced space-time in a way that he informed us, he enlightened us, if you may, that the universe is not only made from 3 dimensions, but it also has a 4th dimension, and that is the dimension of time. And the whole universe is nothing but, some kind of a fabric, which he called a fabric of space-time. Now, if you have a planet somewhere in the universe, then it must have been forming some kind of a well on that fabric of space-time. And the well is actually, it tells you more about the force of gravity. So for Einstein and his theories, the force of Newton is nothing but that can be explained by the wrap of space-time due to the presence of the mass. So mass would actually bend space-time, and gravity is created. This is how he imagined it. And of course, this is a theory which has been evolving with time. And at that time, like even in the 1800s, people were building larger and larger telescopes, and it was mainly the rich people who were, fascinated about astronomy and space and so on, who were investing in building telescopes to make new discoveries. And so, so many of the telescopes were using many of the telescopes, they were able to come up with what we call the time domain astronomy. And you see, time domain astronomy is when you observe stars or planets or galaxies for a long time. So say you're observing a star for a duration of 5 years. So you have seen how that star evolved during the past 5 years. And this is what we call time domain astronomy. And this was very helpful for many reasons. For example, the first, one of the most important groups who were working with time domain astronomy were located in the Harvard College Observatory. And this guy here, Edward Pickering, was he was the manager of the observatory. And he had a group of female astronomers. They were all females. And, all what they were doing, they were looking at, photos for stars or planets or whatever the telescopes observed. And they were trying to compare how stars were evolving with time. They were trying to find any differences that have been, that the star have been undergoing. And at some point, they published a list of 45,000 stars that what they call variable. Variable stars are something like this. These are stars that are pulsating inwards and outwards. So they are changing their brightness. They are changing their brightness, and they have specific period. So say that the star is going to be compressed and then it's going to expand. So the amount of the time taken for the star to be compressed and then expand, it's what we call the period. And I'll tell you why this is important in the history of our understanding of the universe that we live in. And there was a special astronomer out of Pickering's group, and that would be Henriette Leavitt, which was one of the team members of Pickering at the Harvard Observatory, and she was able to detect something called Cepheid stars, and these are again variable stars of some of some nature. Thing is, we have different type of stars. But why are these stars important? It's because once you detect a variable star, you can actually find its distance, and that was very important. Because when these astronomers were detecting these variable stars, they were able to come with different relationships. And this is here you see the period of pulsation on the x-axis and the luminosity on the y-axis. Now the period is how long it takes the star to shrink and then expand again. And the luminosity is more the brightness, because as the star shrink and expand, the brightness will also change. And she was able to find that there's a clear relationship between luminosity and the periods. And this is where the relationship are seen right there. Now, there are other type of variable stars, as I said, and other type are called Lyra stars. And there's many more other stars like that. Now, if you find a variable star, you can find its distance. And when Leavitt was finding distances to these stars, she realized that those stars are really far away. They are outside our universe in a way. So this is when we started to realize that the universe is even larger than we have ever thought. I mean, Tycho, when he saw that new star being formed and then it faded away, he already told us that the universe is larger than we thought. And now, after a few hundred years, we see another discovery which tells us that the universe is much, much larger than Tycho has even imagined. And this expands our understanding of the universe. Until, of course, this famous man, which probably you know about Hubble and his discoveries, what he did is he did observe Cepheid variable stars, and he found distances to them that were really, really even further away than they thought. And eventually he was able to find or to detect that the universe was expanding and that galaxies are moving from each other. And it's even worse that further away galaxies move at even a faster rate. Now, of course, we know that what's really stretching is the space between the galaxies rather than the galaxies themselves. It's just like a balloon. If you inflate a balloon, you will realize that the fabric of the balloon is the one that is stretching, and so any 2 points on the balloon will appear as if they are moving from each other. So this is one point that one has to understand. And of course, he realized after using his new large telescope that our Milky Way is not the universe, but the universe is made out of billions of other galaxies, and these galaxies come in different shapes and different colors and different properties and so on. But of course, they all fall under the same laws of nature that we have here on Earth. So this is how our perspective changed in regards to our understanding of the universe from all the way from the Greeks' time until today. Now, if you dig deeper and talk about the evolution of the Milky Way, one thing you should keep in mind that galaxies like our Milky Way have 3 main parts, and one part would be the bulge, which is the nucleus. This is where you have a supermassive black hole and an overdensity of stars. You also have the disk right there. This is where the sun and the solar system are located. And you have the halo, which is a big area that surrounds the galaxy. And different parts of the galaxy, different parts of the galaxies should be treated differently, because each part of the galaxy was created, some of them were created at different times. So if you look at, if you zoom out from the Milky Way, this is the Milky Way, and what you see in blue here is the halo of the Milky Way. It's one part of the Milky Way, one out of the 3 parts which I just mentioned. So you realize directly that the halo is much larger than the galaxy itself. Now, the halo is what galactic archaeologists try to study. We want to know, how was this formed? How did it evolve? And what is it really made from? And where did the stars that are located inside the Milky Way, inside the halo, where did they come from? This is what we try to answer. And if you look here, you see something, you see the small Magellanic Cloud and the large Magellanic Cloud. And these are 2 smaller galaxies that are, kind of stuck inside our galaxy. So they are part of our galaxy at the moment. And one thing I should mention is that the halo is also dominated by dark matter, which makes, understanding the halo even more complicated. Now, again, the question is, how do galaxies evolve, and how did our Milky Way become so big? If you look at this tree here, this is a map of how galaxies evolve with time. And it goes from, it starts from the top and then it goes downwards. So if you look here, you have, 2 galaxies long time ago, they merged together, they fused together to form a larger galaxy. And then this larger galaxy, it merged with this older and smaller one to form even a more large one. And again, this one merged with another smaller and old galaxy to form a larger galaxy. And the same thing applies here. So what you are seeing here is that, those large, humongous galaxies are actually the results of smaller and smaller galaxies merged together. So at some point, some of the stars inside that galaxy came from this galaxy, or from that galaxy, or from that galaxy. And it's very hard to disentangle which stars came from where, like which star inside the Milky Way came from that galaxy or that one. And this is something which is very complicated to do. And, but with more advanced telescopes and more sensitive ones, we are able to answer some of the questions. And this is why we can see, galaxies of different shapes and types and sizes. So this is the Milky Way, and we always thought the Milky Way is so big, and then you compare it with Andromeda and then with other galaxies. This is simply because this galaxy was a result of more mergers of smaller and smaller galaxies. Now, when we look at our own galaxy, this is our Milky Way, we directly realize that there's a smaller nearby galaxy that, was passing at some point next to our galaxy. And it's always that the larger, the more massive object is the dominant object. And what you are looking at here is how a larger Milky Way-like galaxy can accrete and disturb a nearby moving galaxy. And what you see here are stars that were originally made inside this galaxy, but because they moved closer to the Milky Way, they were accreted and stripped out from their mother galaxy. And this is how it was. It was a normal but a small galaxy, and just because it passed in close enough to the Milky Way, this is what has happened to the stars inside that older galaxy. And you see, these stars are usually the oldest stars in the universe. And this is what we try to do. We try to find these groups of stars, and we try to go back in time and see where did they come from which galaxy, and how old that galaxy was, in an aim of trying to understand, the different galaxies at different times of evolution of the universe. And what you see here is a very detailed map for one of the streams and one of the galaxies that you can see here that was stripped out from its stars. And now we can have very good results about those merger processes that happened throughout the time. Now the question is it easy to detect these mergers? The answer is no. If the galaxy that was accreted is so large and visible and very easy to detect, then sure, yeah, it's relatively easy. But what if the galaxy was faint, or what if the merger happened long time ago that it didn't leave any observable signatures? So things really get complicated. So let me show you what kind of studies we actually do to find these signatures of mergers. Remember what I told you about galactic archaeology? We try to find how galaxies evolved. So we try to look for a group of stars. If you look at this image, you see the eccentricity on the x-axis. Think about eccentricity as, the motion, how those stars are moving. So these dots are stars, okay? And so this tells you more about how the stars are moving. On the y-axis, it's telling you about what we call metallicity. So it's Fe/H. It is the ratio of iron and hydrogen. Now, if you want to simplify the meaning of metallicity, you can think about it as H. You see, the stars that were born in very, very old galaxies are usually metal poor. They don't have a lot of matter. You see, the universe needed some time to evolve to start producing more and more metal, especially with supernova. And this is why you would expect that stars that were born directly after the Big Bang or sometime after the Big Bang, they didn't really have much metals because there wasn't supernova explosions yet. So you expect them to be metal poor. And the newer stars that are born today in our Milky Way, for example, or in other systems in the universe, they usually are metal rich. So stars that are located here at the lower part on the y-axis are metal rich, and vice versa. Stars that are here are metal poor. So these are old and these are newborn stars relatively. And you can directly see that there's a group of stars right there, and there's another group of stars on the other end of the graph. And this tells you that these two groups of stars were formed at different times, and they have different compositions and different properties. So, and these stars are all located inside the Milky Way, and you expect that all stars in the Milky Way to have the same properties, but obviously these don't share the same properties, because this one must have came from a different galaxy from outside the Milky Way. And after a few years, there was a survey called the Sloan Digital Sky Survey, and it was able to also detect these two clumps of stars, and that was the proof that, okay, now we can really tell that there are different stars of different ages inside our own Milky Way. If you want to move further, you could also find these group of stars in different 2D plots. For example, on the x-axis here, you see the location of stars. On the y-axis, you see the distance of stars. And you can see that there's one group of stars here, which came from a dwarf galaxy that was accreted. And you have another group which came from another another host galaxy or a dwarf galaxy. And this makes things complicated, because if you have one galaxy being merged with the Milky Way, it would be easy to detect it. But what if you have hundreds of mergers? How can you differentiate those stars? And this is why I'll be talking a bit about halo stars and the importance of studying halo stars here. This plot here is a velocity plot of stars. Everything inside the circle are stars located in the disk, just like the sun is located in the disk. Everything above that line are the halo stars. So when you look at this image, you wouldn't see any difference here. But as I told you before, we expect that the halo stars to be metal poor, because they are really old. So if we study the metallicities of these stars, the halo stars located here, you realize that some of them, especially the ones in orange, are actually metal rich. So the question is, how is it possible to find metal rich stars that are young in the halo, when we always thought that the halo was formed from old stars that were accreted from from other places in the universe? You see, it doesn't matter really if you know what Vy is and what Vxz is, but I'm just trying to to tell you that the most important thing here is that we always expected that these stars that are in the halo of the Milky Way to be very old and metal poor. But when we observed them, it was shown that many of these stars are metal poor indeed, but some of them are metal rich. And the question is, where did these metal rich stars come from? They cannot come from another galaxy, because those other galaxies are very old. And so one thing you could do is you can compare your observed data. So this is the data that we have seen with telescopes, with simulated ones. And with simulated data, you can, in this region, you can see that some stars are indeed metal rich. And this just to confirm, the results that some metal rich stars are young and are found in the halo. So how was that possible? Well, we know today that some of the stars are formed and born ex situ, which means they were born in different galaxies to be accreted inside our galaxy. And stars are formed in situ, so they were formed inside our galaxy, but later on they were kicked out to the halo. Mainly they are formed in the disk, and for some reason they were kicked out and they got stuck in the halo. So this is really what we have come through. And if you look at these two simulations, this is simulation for in situ stars that were born at the disk and got kicked out to the halo. You see they are centered at the center, at the middle. And for those stars in the ex situ that were accreted, you see that they are distributed and they are more located at the outer parts of the halo. If you look furthermore about, in these 2D plots, on the x-axis, you have galactocentric distance, and on the y-axis, you have the age. This is for in situ stars. Now, I'm sharing these images because, usually I wouldn't really share such images, but I just wanted to share with you how can astronomers get real data, analyze it, and come up with conclusions. So if you just follow up with me on this one, let's say, these are the in situ stars born inside the Milky Way and that were eventually kicked out to the halo. This is the galactocentric distance, which is the distance between the disk and the halo and the star. So if it has a large number, then it is really far away from the disk. And this is the age of the star. You realize that in situ stars that are in the halo, they are actually closer to the disk of the Milky Way because they do not go further than, this region. They don't go into further away distances from the disk. And they were also born at all times. So we have metal-rich stars that were born and got kicked out to the halo in the past 12 billion years. So this is not something new. But when they get kicked out, they don't go further away in the halo. They keep at a fairly close by distance to the disk. Now, if you look at exotstars that were accreted from other galaxies, you will realize that all of these stars came long time ago, between 8 and 12 gigayears. So our Milky Way accreted them 8 to 12 gigayears ago, but they cover all distances. They can be close to the halo and they can be really further away from the halo. These are the images, these are the data that we look for to come up with conclusions and to come and tell you that this is how the Milky Way evolved and so on. So this is what really matters in these plots. And finally, this takes me to the last part of my presentation, stellar streams with Gaia, which is of course connected to everything I have just mentioned. But it's good for you to know that the most used, and if you think of Hubble Space Telescope, it was and it's still like a very huge mission, which allowed us to find so many things and to discover a lot about our universe. But now, and then at some point there was another survey, and right now it is all about the Gaia Space Telescope, the Gaia mission. This is a space telescope. It's located in space now. It not only observes the stars and the galaxies and everything there is. It not only gets the colors of those objects, but it also gets the proper motions. Now, maybe you don't know what a proper motion is, but the proper motion is mainly the direction of stars, how the stars are moving, in which direction. And this is something very, very difficult to get. And I will show you an example about proper motions in the end. So this Gaia is very important because it gives us a 6D information. Usually the other telescopes would give you 3D information, mainly positions and colors. But this Gaia mission gives location, colors, as well as velocities, which gives you the proper motion, a very, very important property of stars that help us greatly understand so many things in the universe. And remember, this is a new telescope, and new data is still being released every now and then. Just to show you an example, so on the x-axis you have the magnitude. The more you go to the right, the deeper and the fainter the object, so it's harder to find. And you see that Hipparchus, which was a survey and it's a catalog, was able to find stars in this region, which was fairly bright stars with magnitude of 12. But as Gaia was released, the new data, now we are able to see stars that are further to the right. So these are fainter stars that and more parts of the Milky Way, and to go deeper and beyond the Milky Way, of course. Remember, I told you before that I mentioned that if there was only one galaxy being accreted by the Milky Way, then it wouldn't have been very difficult to actually tell where did it come from. But in the simulation, you can see so many galaxies, hundreds of galaxies being merged with the same galaxy. So it's very complicated to tell which galaxy came from what other galaxy. So if you look here, this is a simulation. This is the Milky Way being accreted by the Milky Way. And right there in purple, you see another dwarf galaxy which just appeared. So now we have the Milky Way accreting two galaxies. And in pink, which just appeared right there. So how is it possible for us to differentiate the pink from the blue, from the purple galaxy? This is the challenge. When you use the energy right there. and stars will be conserved, and you will realize that stars that came from that dwarf are clumped and grouped together, and energy phase. And the same thing applies for those proofs that could be discovered. And so this is at first, like, this was published in 2006. That in the Milky Way, in the halo of the Milky Way, most updated. This is the most updated map that shows all stars that are located in the similar telescopes. This wouldn't have been possible. So this is how astronomy has helped us to really be very active. This is the Milky Way right there. This is where the host galaxy was, or the dwarf galaxy was located. This is the leading arm of the galaxy, which is leading the accretion process, and this is the trailing arm right there. And this has all happened in the past 3 giga years or so. And a few more things about the different discoveries in the halo. If you look at this plot, this is color magnitude diagram. If you are familiar with this, you could see. So this is one of the images that that let us discover a very new and a huge dwarf galaxy inside the Milky Way, which is called the Gaia Enceladus, or the Gaia sausage. What you see here is a color magnitude diagram, and you see that there's a population. Oops, sorry. There's a population right there and another population right there. Now, I don't know if you know what that means exactly, but what this is giving you, this line is telling you that this is a group of stars that have the same properties and age, and there's another distinct and strange group of stars located right there, which is even older than the halo Milky Way stars. And when you plot the metallicity plot right there, you would realize that these stars that are grouped here have a distinct metallicities, so they have different in these images. Anyway, if you look at more plots, you will just be seeing more and more proofs, and this is what you see in a velocity plot. So what these images, it told us that the Milky Way, a huge galaxy in the past, and these are the arrows that are showing how the stars from Gaia and Enceladus are moving right now in the Milky Way. So these were all actually part of another galaxy that visited ours. This is not something easy or straightforward to do, but something this has occurred, like the accretion has occurred 10 billion years ago, and that the mass of that galaxy was around 1/4 the mass of the Milky Way. So it was a huge one. And if you're familiar with the globular clusters, we now believe that were born in Gaia Enceladus, and then they were accreted by the Milky Way. These are stars located in the sky. This is a cluster located right there. Now, when I study the proper motion, it seems to be moving in this direction. And these orange stars are, of course, and this is what we expect. Now, if I try to calculate the motions, proper motions of all of the stars around the globular cluster, this is how it will look. You see some stars are moving in different directions. Let's look at this star moving in that direction, but the globular cluster is moving in that direction. Now, just getting to the point for you to find the proper motion wouldn't have been easy without data from telescopes, of course, because this is not something straightforward then you can do. You can just draw arrows and say this is how the star is moving. It's more complicated than that. So I'm trying to see which stars, just that you know, what I'm trying to do is I'm trying to see which stars in this image might have escaped from the stars in the halo of the Milky Way, might have escaped from other from other dwarf galaxies. So the question is, are there stars here in black that originally escaped from the globular cluster? So let's do this again. We see the proper motion. This is the proper motion of all stars in the image. And you know, if you just remove stars that have different directions, two stars stand out, this one here and another one right there. And if I remove all stars, it seems that these two stars actually escaped from that we do to try to find what we call the escape. When you look at other papers, you realize that, you know, there's a stream of stars located in this brown band and so on. So the more data you have, the better analysis you can do. And of course, everything I mentioned today, like I just wanted to share some, you know, some techniques and scientific ones that astronomers usually use to to find signatures in the Milky Way. Of course, we can apply this same analysis to other stars, to other galaxies in the universe. And you know, see that Andromeda, when you point your telescope towards Andromeda, you see it coming towards you. So, the two galaxies will merge to form even a larger galaxy that we're going to see, and more massive than our own. So thank you for listening, and you know, I'm happy to answer questions you might have.
Thank you, Dr. Abbas, for this very interesting topic and talk. It was a pleasure receiving you today, and we will start by asking the question we have on the chat. And I remind all, if you have any question, please raise your hand and you can ask directly your question to Dr. Abbas. I will start by from Malak Abdul Hassan. So is there a possibility for our Milky Way to merge into another galaxy? How would this disturb or affect our solar system? Dr. Abbas, are you with us? Hello?
Can you see me? Hello?
Yes, we can see you, and now we can hear you.
Can you hear me? Okay, perfect. So I was saying that the last slide I showed two galaxies, merging together, and it's for sure that our Milky Way is going to merge with Andromeda at some point in a few giga years, and they're going to merge to form one larger galaxy. Now, is there anything that's going to happen to our solar system? A trivial first thought answer for someone who doesn't know how the universe really works would be, of course, like the planets should collide with other planets, stars should collide with other stars, and so on. But in fact, believe it or not, when galaxies merge together, it's very, very unlikely. It's very unlikely for any stars to even merge or collide. This is because the distances between stars is very massive and very huge. So the probability of stars colliding or our solar system colliding with another solar system from Andromeda is almost zero. So the answer is statistically there's a 99.9% chance that nothing will happen to our solar system. So and this is how it is. I mean, the Milky Way can fit trillion to the trillion of stars, but in reality, it only has 100 billion stars, but it can fit much, much more. So most of it is empty.
Okay, the second question is from me. Do all galaxies have a supermassive black hole on their center? And do supermassive black holes exist into the intergalactic space all by its lonesome?
So do all galaxies have supermassive black holes in their center? Yes, usually yes. All spiral galaxies are, they have a supermassive central black hole at, in their bulge. This is something that was discovered not so long ago either. And what was the other question? Are there black holes?
Yes, into the intergalactic space all by its own. Any stars orbiting them or something like this?
Well, mainly, you see, if you think about it, black holes are the result of dead stars, right? When you have very massive stars, when they die out, they explode, the supernova, and they end up being a black hole, right? So if there are stars between the intergalactic space for any reason, then there could be black holes. But usually black holes are really more.
Okay, we got cut maybe, but the answer is here. Okay, there is a comment here from Sam Busaba. From now to 800 million won't exist on Earth because the sun will be big enough to evaporate the seas and kill the life on Earth. So we aren't going to witness the collision unless if we travel to other solar systems. So this is just a comment. Do you have any comment on this and a clarification? Is it 800 million years or more?
I agree with Sam. Yeah, I mean, optimistic because it's going to be probably and and if you speak about 8 million years and 4 billion years, there's a big difference, and who knows what's going to happen in these years. But yeah, eventually the sun will die out, and it will eat up our planet.
Okay, Perla Dahir, from now to 100 years, we won't exist due to climate change, and we invite you all also to follow the week of World Space Week, because we will have talks about climate change. Is there any question from the participants to Dr. Abbas? Okay, so we thank you a lot, Dr. Abbas, for this very interesting talk, and wish you also good luck in Dubai. I guess you are in Dubai now, and unfortunately we have to leave Lebanon sometimes, and wish you will be there not for long.
Thank you, Jean-Pierre, and thank you, everyone, and thanks for listening.